Welcome. In this video, we will talk about piecewise functions, and we're going to try to analyze them using limit notation. So now, let's start by taking a look at this small introduction question, which states, let's take in consideration the following piecewise function, and we want to describe the piecewise function in our own words. We would like to use the word domain and range in our description. So here, this is what we call a piecewise function. Let's try to understand how to read a piecewise function. Well, notice that this piecewise function has two lines, and every line talks about a different function. So it is a big function made out of little functions. And my first line refers to a function, which I'm going to call y1, whose function is being defined as just x. So the first line, it talks about the line y equals x, but now this line has a limitation or a restriction. And this restriction is saying every time my value of x is greater or equal to 0, I'm going to be graphing the function y equals x. And the second line, it's saying, which I want to call it y2. The second line is saying, look, I'm going to have a function which I'm going to define as just negative x. But notice that it has a different restriction. The second equation is saying every time x is less than 0, I'm going to be graphing the function negative x. So notice that here we're talking about two different functions, y equals x and y equals negative x, but each of those functions has a small restriction or limitation on it. Well, let's actually visualize this. So let's actually graph this. So let's start by graphing the first line or the first function y equals x. So we're going to be graphing the function y equals x, which is just a linear function whose slope is 1. So it should be looking something like this. So here we have the function y equals x. But notice that we don't want the whole function because there is a small limitation on it. And the limitation is saying I only want those values when x is greater or equal to 0. So notice that we're just looking at this region. So here we have x equals 0, but I only want those values that are greater or equal to 0. So therefore, I only want the right-hand side of this function, if you want to think about it that way. So what happens to those values on this function that does not fit this description? Well, what's going to happen to those values is we're not going to use them, or we're just going to erase them. So now notice that what is left right now, it is exactly what we needed. We know that this green line, it's a section of the function y equals x, but notice that we're only graphing those values that are greater or equal to 0. So that takes care of the first section of the piecewise function. So now let's graph the second section of the piecewise function. The second section of the piecewise function is saying graph the function y equals negative x. And let's just do a rough sketch. So this is just a linear graph whose slope is negative 1. So it's going to look something like this. So notice that here we have the function y equals negative x. But we don't want to leave the whole graph. Notice the small limitation that we have here. We only want to use those values that are less than 0. So all these values where x is 1, 2, 3, 4, 5, they're greater than 0. So therefore, I don't want to use them since it does not fit the description that we need. So what's going to happen to those values? We're just going to erase them here. So we're just going to erase those values that do not fit the domain restriction. Again, we want to have a good eraser here. All right. And let me actually just move this here to the top, just to indicate that this is the function y equals negative x. And notice that now what we have left here, it is exactly what our piecewise function is saying. Because notice that here we have a function, which is defined as y equals x, which we're only using those values that are greater than 0. And here we have a function y equals negative x, and we're only using the values that are less than 0. So now the whole picture that we do have here is the interpretation of the overall piecewise function, which is what we wanted. So this function y equals x is represented by the whole thing. And now let's just describe what this function, let's try to describe this function. So we seem to be having some kind of a B shape, which notice that this is kind of like the graph of an absolute value. So if we would have graphed the absolute value of x, we would have got this same shape. But now, what is the domain? What is the domain of this function? Well, notice that the first section of my piecewise function is using those values that are equal or greater than 0. And the second piece of the piecewise function is using those values that are less than 0. So therefore, my overall function is using all possible values. So in that case, the domain is all real numbers, aka we can say that is from negative infinity to positive infinity. So what's the range of this piecewise function? Well, the range, remember, the main is all x values that are possible in our graph, and the range is all the outputs or all y values on this graph. So notice that the way that we graphed it, this green section, which is the function y equals x, is going to just keep increasing without a bound. And the blue section, which is y equals negative x, is just to be increasing without a bound. So notice that we're only using those y values that are equal or greater than 0. So therefore, my range are all those values which are greater or equal to 0. Or we could just use the following notation. So 0 towards positive infinity. So what about the limit of this piecewise function? Can we perhaps identify a point where the limit does not exist? Well, notice that all values in this piecewise function, the limit will exist. Because let's just choose a point. Let's choose this point. That seems to be negative 1, 2, 3. It seems to be negative 4. So what happens to this function? Are we getting closer to 4? Well, from the left-hand side, we're approaching this value. And from the right-hand side, we're approaching this value. So therefore, from the left and from the right, we're always approaching the same value. So the limit exists here. So how about over here when x is negative 2? Well, from the left, I'm approaching this value. And then from the right, I'm approaching this value. So the limit will exist at negative 2. And it doesn't really matter which points we choose. I'm always going to be approaching the same value from the left and from the right. So therefore, in this function, the limit exists at all points. And what I mean by all points, I mean all x values in the function. So choose any value in this piecewise function, and the limit will always exist because we will always be approaching from the left or from the right in all the points in our graph. So this is how we want to read a piecewise function. It is a big function made out of little functions. And every little function is going to have a certain limitation, or what we call a domain restriction. And once we glue them all together, we get the overall picture, which is the piecewise function. So let's take a look at something a little bit more challenging here. So here notice that, at least we're not looking at the very simple piecewise function, which is just x and negative x. We seem to be having a little bit something more complicated here. But still, let's graph the following function, and let's try to identify the domain and range of the piecewise function, and let's define the following limits. So let's graph this. So the first thing we always want to do is just graph the function. And again, let's take it one step at a time. Let's take a look at the first line. Now the first line is telling me I have a function which I'm going to be defining as negative 6. And this function will only occur for those x values that are less than negative 2. So let's graph that. Let's start by graphing just the overall function y equals negative 6. So here, this green line, let's try to make this a little bit more straight. So here, this green line definitely represents the function y equals negative 6. And again, we don't want the overall graph. We don't want the whole graph. We're only interested on those x values that are less than -2. So here we have -2. This is where my graph meets when x is -2. And we're only interested at those values that are less than 2. So all these points that are on the right hand side of -2, we need to erase them because it is just not part of the piecewise function that we want. So all we got to do is here, going to -2, we only want those values that are less than -2. So therefore, all those values that are greater than -2, we're just going to erase it. And very important here, because now the endpoint at -2, notice that this is just defined as x is less than or equal, less than the -2. So therefore, we're not allowed to choose the value at -2. So therefore, in this piecewise function, at the location of -2, we need to have an open circle. If the function would have been defined as less than or equal than -2, then we would have a closed circle. Well, since we are not allowed to choose a value of -2, we got to leave it as an open circle. So that takes care of the first line. So now, let's take a look at the second line on my piecewise function. My second line of the piecewise function is saying, I'm going to be taking a look at the function x plus 1 to the fourth. So let's graph that. So let's go to our decimal activity here. So notice that here we have the function x plus 1 all to the fourth, which is what we wanted. So this is the function of x plus 1 to the fourth. So notice that, let's just pick some points. It seems that we have a location at -1 comma 0. So let's just put that in there. We also seem to be having a location at -1 comma 1. So let's put that in. Seems to be having a location at -2 comma 1. So at -2 comma 1, we have another point here. And we also seem to have another point at x 0 comma 1. So we have another point there. And we seem to be just, and again, this is a rough sketch. We need to just have some kind of a parabola facing upwards. So this is the overall function x plus 1 to the fourth. But notice that we have a small limitation on it. And this limitation is that we only want those values that are greater or equal than -2. So therefore, all those values which are less than -2, we need to erase them. So on this red function here at this location is when x is -2. So all these values that are less than the -2, we need to erase them because it doesn't fit this description. We only want those that are greater or equal to -2. So let's just erase that. And very important, now notice that in the second line, we have x is greater or equal to -2. So therefore, in my second function, I am allowed to use the value -2. So therefore, at x equals -2, we need to have a closed circle. So now this overall function, the combination of these two, is the actual picture of my piecewise function. Because again, the piecewise function itself is when we glue, or is when we put together all these little functions with its own little limitations. So the piecewise function is the overall graph that we do have here, which is a combination of those two. So let's analyze it now. So now that we have a better picture of what's going on this piecewise function, let's try to analyze the domain of this function. So remember that domain, we're going to be looking at all the possible x values. So let's see what x values are we allowed to choose. So let's start by looking at the function on the left. So notice that this function still extends. And as we're going to the left-hand side, we're still on the value y equals -6. So notice that here, we're using all the points from -infinity all the way to -2. Again, I'm just looking at the x values. So from -infinity all the way to -2, we're allowed to use all those x values. But the moment that we hit -2, we're going to the other piecewise function. And from -2 all the way to positive infinity, because notice that this function is keep going up, but we're also moving to the right hand side. We're also using all those x values. It's not like we have a gap here. If we would have a gap, then we would not be able to use those x values. So take a look that we're allowed to use all possible values. We're allowed to use all possible values when it comes to x values, because from negative infinity all the way to -2, we're using all those x values. The moment that we hit -2, we're still using the value of x equals -2, but we're using it up here. And as we keep moving to the right, my function keeps increasing, so therefore it is defined, and I'm still going to be increasing, I'm still going to be moving to the right hand side, so I'm still going to be able to use those x values that are on the right hand side of 2. So therefore the domain of this function, it is all possible x values. Therefore we can just define it as negative infinity to positive infinity. Now I would like to make a small pause here because I want to address what's going on here. Because you might be saying, well, we have a open circle here. So how come we need to include this value on my domain? How come we're allowed to use -2 here, where my first function is not allowed to use in it? Well, we're looking at the overall picture here. So even though -2 is not used on the function -6, it is used at the function x plus 1 to the fourth. So therefore, in the overall picture, we are using the value at -2. Now, if we were to switch this problem a little bit, so let's say that we would have changed this to being greater than 2, and if it's greater than 2, we would only be using, we would be using an open circle. Now, if we would have this case, then notice that neither function is using -2. So if we were to have that case, let me call domain 2. If we were to have that case, we're not allowed to use the value of -2. So therefore, my domain would look a little bit different. From negative infinity up to -2, we're not allowed to use -2, so we're going to jump it from -2 to positive infinity. We would be using all possible values except -2. So notice that that little change, just a little line right here, changes the meaning of my overall piecewise function. But again, this is not the case that we have here, but I just wanted to make that small distinction on this example. So let me just erase that and let me go back to how the problem started. All right, so now we're back. Notice that everything changed to how it originally was. So now let's move on to range. Now range talks about the y values. So let's take a look at, are we allowed to use all y values? Well, notice that in this case, we are always using the y value of -6. And on the second part of the piecewise function, we're only looking at those y values that perhaps are greater than 0. So what is the actual range of the overall piecewise function? Well, let's start by looking at the lowest y value. Well, it seems like the lowest y value that we're using here is -6. And what seems to be the highest y value that we can use here? Well, notice that at least the red function, it is going to positive infinity. So it seems that we're always going to be increasing without a bound. So therefore, the highest y value, it is positive infinity. And you should stop at this moment because this is not correct. Because at least one, well, we're missing a comma here, but at least one common misconception that I've seen from my students is that we always use the lowest y value as on the left and the highest y value on the right. But this does not really represent what's going on here, because notice that we're not even using the values from here. We're not using -4, we're not using -2. So here we have no y values. But here we're indicating that, yes, we're actually using them. So this is just a small misconception that I wanted to address here. So what is exactly the correct way, or at least one way, to write down the range for this function? Well, we know that the lowest y value, it is still -6. And again, this is going to be a very weird way to just write our range. So we are allowed to use -6, But notice that we're not allowed to use any y values between -6 to 0. So therefore, I am going to exclude it. And notice that I'm going to be saying that I'm allowed to use any y values from 0 to positive infinity. So now this is one way of writing the range. This is saying I'm using all y values from -6, and then I'm going to be jumping from -6 to 0. So therefore, I'm not using them. But I am going to be using all those y values from 0 to positive infinity. So from 0 to positive infinity. So now let's analyze this function using limit notation. So let's take a look at the following here. What is going on to this function g of x as x is approaching negative infinity? So what exactly do we mean by this notation? Well, what we mean by this notation is we're going to take a look at the behavior of this function as x is getting infinitely smaller and smaller on value. So therefore, I'm just going to be seeing what happens to the function as my graph is just getting farther and farther to the left-hand side. So let's take a look at both directions. So if I'm approaching it from the right, notice that I'm going to be just following this curve here. Once I get to -2, I'm going to drop. As I keep getting closer, as I keep getting closer and closer to negative infinity, or as I'm just moving on to the left-hand side, notice that I'm still going to be on this function y equals -6. So as I'm getting farther and farther to the left-hand side, notice that I'm still going to be on the value y equals -6. So therefore, the limit of g of x, where g of x is a piecewise function, as x is going to negative infinity, well, that's equivalent to -6. Because as I'm getting farther to the left, I'm still going to be on this function. So therefore, as I keep getting farther to the left, I'm still going to be in that function. So therefore, I'm still going to be on the value -6. So what happens to this function as x is going to positive infinity? So what happens to this piecewise function as I'm moving farther and farther to the right, or x is going to positive infinity? X is increasing in value. Well, if I'm getting closer to the right-hand side, so let's look at it from the opposite direction, which is from the left. So if I'm moving from the left going towards the right, I'm going to be on this function. But once I get to -2, I'm going to jump to the other function. I'm still going to be moving farther to the right-hand side. And if I keep moving farther to the right-hand side, what is the y value that I seem to be approaching? Well, this function is increasing without a bound. So therefore, if I keep moving to the right-hand side, my y value is going to be increasing without a bound. So therefore, we're going to say that as the limit of x is going towards positive infinity, well, my y value is increasing without a bound, so the limit is positive infinity. Because again, the result of those limits, you should look at the y values as x is having a very specific behavior. So now let's take a look at this function still, but now let's try to define the limit as x is getting to a very specific point, which is -2. So let's do that in blue. So first things first, where is -2 on my function? So here we have -2. And there's something interesting happening at -2. And that is that if I'm approaching -2 from the left-hand side, I'm going to be looking at this direction. So as I'm getting closer to -2 from the left-hand side, notice that I seem to be getting to the value of -6. Now, if I'm going to be approaching still the value of -2 from the right-hand side, notice that I'm going to be on this red piecewise function. So if I'm getting closer and closer to the value of -2 from the right-hand side, I seem to be approaching the y value of 1. So if I'm coming from the left, I'm approaching the value of -6. And if I'm approaching from the right, I'm approaching the y value of 1. Notice that they're not approaching the same y value. So therefore, the limit does not exist. Because recall, for the limit to exist, we have to be approaching the same value from the left and from the right. So here is -2. If we get closer to -2 from the left, I'm going to be approaching the value of -6. And if I approach -2 from the right, I'm going to be approaching the value of 1. They're not the same y value, so therefore the limit does not exist. And the last thing that we want to discuss about this question is g of x continuous at x equals -2, which is what we have here. Well, notice that at -2, we have this big gap going on here. Because on the left, as we got closer to -2, once we got to -2, we jump to the other function. So notice that we did this big jump coming from here, then we jump to here. Anytime that we have this jump, we can say that the function is not defined at that very specific value. As a matter of fact, we have a name for that. So the answer is no. We have a jump discontinuity. At the value x equals -2. And why do we call it a jump discontinuity? Well, because we jump in places. So we have here, once we got to -2, we did this big jump. So that's pretty much the reason why it's called jump discontinuity, because we jump from value from from -6, we jump just drastically all the way from -6 to just +1 out of nowhere. So whenever we have those scenarios where we jump from one value to another, then we can say that the function is not continuous at that point. So the last example that I wanted to discuss is to do quite the opposite, because in the first two examples, we were given the piecewise function and we graphed it. But now we're trying to do a small example where we actually do the opposite. Here we've been given this function, y equals the absolute value of x minus 2. And our job is to see if we can rewrite this function as a piecewise function. So if we were to graph the function absolute value of x plus 2, we would have got the following. So we're going to have some kind of a B shape, center at -2, and it's just going to be 1 point to the right, 1 up, 1 right, 1 up, 1 right, 1 up. And the same goes for the other side, 1 left, 1 up, 1 left, 1 up. So this function that I just sketched here, this will be the function of the absolute value of x plus 2. So now what we want to do is see, well, is it possible for me to perhaps rewrite this as a piecewise function? And again, let's call that piecewise function g of x. Can I pretty much just take this function apart and write it into smaller functions? Well, the first thing that we want to see is into how many pieces can we break down this function? Well, I can see one thing here. I can call this one section of the graph. Actually, I'm just going to write it here. I can see that this is just one section of the graph. Now, if I kind of like ignore the section going on here, and I just concentrate on the section that I just highlighted in yellow, let's just extend this line. Let's just extend this line just for illustration purposes. Where again, this dotted line is not part of the initial, but I want to extend it because notice that if we extend it, it is clear that we have a line, a straight line, and it is a line which has a slope of 1 and it has a y-intercept at 2. And this line can be represented as just y equals x plus 2. It is a line which is a y-intercept at 2 and a slope of 1. So therefore, I can just rewrite this right-hand side section as just x plus 2. But now, okay, so we have defined the line itself. So now let's take a look at the restriction. What x values are we allowed to use in this line? Well, notice that we're only allowed to use those x values that are greater or equal to -2. Because notice that in this section, we're only just using those values that are on the right-hand side of -2. So therefore, I can say that I only allow to use those values which are greater or equal to -2. And all we did here, we just broke down the function apart. So we have broke down the first section here, and we have just seeing that it's just nothing more than a straight line. So what happens to what is left in this function? Well, let me just highlight it in green. Is it possible for us to write down a function that will describe this section of the line? Well, it's not as straightforward as we just did with the yellow highlighter. But one thing that we can do here is that we can definitely see this is nothing more than a straight line. It is a straight line who has a slope of -1. So let me just extend this. So one down, one to the right, one down, one to the right, one down, one to the right. So let me just extend that. And now we can see that this section in green, it is a straight line with the slope of -1 and a y-intercept at -2. So therefore, we can just describe this as just y equals -x minus 2. But let's be careful here. What x values are we allowed to choose? Well, we're allowed to choose all those x values that are less than or equal to -2. And now notice that all we have done is we have rewrote, we just rewrote the function that we were given into a piecewise function that we do have here. All we did, we took a look at the overall function and we broke down into pieces. And we just rewrote that piece individually here. Now, before we conclude, I do want to make a very small point here. Notice that in both functions here, we're using the value of -2. So on the section on yellow, we're saying x is greater or equal to -2. And on the green section, we're saying that x is less than or equal to -2. In both functions, we're using the value at -2. That's not okay for us to do that. So one easy way to fix this is, since we are the ones who are defining this function, we're allowed to choose which one we wanted to have a value at -2. So I'm just going to be choosing one of them. And that's fine, because this one, the one in green, it has a hole, and the one in yellow, it fills it in. So therefore, the function itself has a value at -2. And that's one easy way to fix this. Now, this is the correct interpretation of this absolute value function. Notice that all we did, we just broke it down into pieces. We wrote each piece individually with its correct domain restriction. And that's how we can properly write down a piecewise function when a function is being given. And with this, it concludes our lesson on piecewise function using limit notation approach.